Afternoon, folks. I'm going to talk about combining ARMs and RISC-Vs in a system and sort of issues that we'll see and why you need in-life monitoring system. So let's start with a problem statement. I would claim it's not about the ISA. There's going to be different kinds of ISAs throughout your SoC. And it's not about the core either. There's going to be several different kinds of cores, and they all have different purposes, and that's why people will use them. And of course, we already know that compute is solved. The cores are solved. You can easily, people can create cores, but the product, i.e. a system, is what matters. And so the challenge is that complexity, systemic complexity is the problem. This comes from ad hoc programming paradigms, sometimes no programming paradigm, different kinds of processor interactions, hardware-software interactions, strange interconnects, and not to be forgotten, the system isn't architected. One extreme case is one of the previous companies I worked for, the acquiring company was acquired, sorry, the company was acquired, but the acquiring company, they had an architecture for a chip, an SoC, which looked like somebody had got hold of the company credit card and bought lots of IP off the internet and stuck it together. And so they were a bit surprised that this didn't work in the field, and lots of customers complaining about it. So you need to architect the chip, and that means modeling, and then once you put it together into the system, you need to understand how it's behaving. So a typical SoC looks like this, has some sort of interconnect, pick your favorite processors, and as we're seeing, lots of RISC-Vs, but we're seeing heterogeneous systems, and that will continue for a very long time. Even with RISC-Vs, there'll be heterogeneous systems. So you have an interconnect, some processors, and a DRAM controller and the like, all hanging in some sort of SoC. What is required is some level of processor-centric debug system. So you need some route into the system, and then these various different cores will have different types of debug interface. So whatever processor-centric system you have for your debug, monitoring, and trace has to handle that interface. In addition to that, what you need is monitoring of interconnects, so you can observe how transactions are behaving. You'll need some way of faster I/O other than JTAG off the system. Other kinds of monitoring IP, static instrumentation, logic analyzer. That's this status monitor. But as the system's getting more complex, you'll also need some way of having all this data that you collect and generate going to an on-chip analytics system. I'll give you some examples in a little while. So you don't use all those blue blocks, but in many systems, you probably will. So what UltraSoft does, this is my company, what we do is we provide a coherent architecture. So it's core neutral, processor neutral, and provides a coherent architecture for debug, monitoring, and analytics. The IP is highly parameterizable at silicon time. The IP that you lay down is that you can configure it at runtime for different scenarios. And then because we're monitoring the system at runtime, you can use that to look for activity that should happen, that hasn't happened, or activity that has happened, that shouldn't happen. And then the data that these analytics modules generate is rich, it's small in terms of bandwidth, so you can pass that to an analytics subsystem or I/O off chip. Before we go into problems of creating ARMs and RISC-V systems, let's look at something where you have control over what the programming paradigm is. So you're not carrying any legacy system. So this is an architecture of a system that it was a clean sheet. We had control of the programming paradigm, control over what the interconnect was. And in this case, we had a novel interconnect. The processor, it's a sea of processors. A software-defined radio is targeted at the base station market. The communication allowed for point-to-point, point-to-multipoint. The program model was a CSP, so each processor, the P stand for processor, each processor had its own compute. And the communication was done in CSP fashion. The communication was a TDM bus, and periodically the connections changed and realized the virtual connections to real connections. What this meant was you efficiently used the bus, and you could scale that off-chip, as in here, and this allowed for a system with up to 64, the biggest was 64K processors. Because you had the compile time interconnect, you had no runtime arbitration. If it compiled, statically compiled, that meant your system would operate in a deterministic manner. And so you could exploit that by taking the sea of processors here, instantiate some software functions like Viterbi's or turbos, and then the next generation of the chip, you hardened it and used the same verification suite as you did for the software implementation. That meant you got a shrunk, you saved on your verification time, and you got a smaller die. Now, notice the later chips, the ARM processors came in. So this still exists, and we had control of the programming paradigm. For the target application, it worked fine. So let's look at some examples where you don't have control over, as much control over the programming paradigm and interconnects. So what we need is some tools. The tools need to support heterogeneous architectures. So not just ARM-based architectures, not just RISC-V-based architectures. So this is the architectural modeling should support that, and the data that you collect at runtime should be able to feed into these architectural tools. So you can close the loop as from what you'd started out to design is actually what you got and gave the performance and the functionality that you set out to achieve. There needs to be a true heterogeneous tool chain, not separate, one for ARM, one for RISC-V or MIPS or whatever. It needs to be a coherent tool chain, and this is especially important for debug, for the debugging tools. And the GDBs and OpenOCDs need to handle this in an efficient manner. I know there's work going on to do this, including my companies doing that, but we need to make this happen. And strangely, not everybody likes open source. So commercial vendors need to get involved as well. And importantly, for debug, you want one cockpit. You don't want one cockpit for ARM, one cockpit for RISC-V, and one cockpit for SoC information. So you want one cockpit. And we need tools that help with visibility of the SoC as it's operating. And as complexity continues, because it's not going to stop, we need a way of automatically analyzing the target system, looking for anomalous, doing automatic anomalous detection, so to help engineers understand and debug their SoCs. So let's take an example here. This is, those of you who've worked with ARMs, this is a pair of A-class ARMs, and the NOC is a CHI NOC. And in this case, the customer used a RISC-V core that they brought in, and so the interface, there wasn't an inherent CHI interface, so it had the bridge. So, the cores that we have need to support the native interconnects there. So, yeah, tiling's great, but we also need to be able to support existing NOCs out there. And I don't think ARM's going to change tiling anytime soon. And CHI is a spec, so people implement it in different ways. So you could have crossbars or rings. So whatever system you have needs to support that. So first, we need a run control. And the run control that we have needs to support the various different kinds of interface to the cores. So you don't want to have one for ARM, one for RISC-V. So you need to have a unified approach. So you may have the interface coming in from the outside world may be different to the interfaces that the cores have. So the blue structures need to abstract away from that. This blue block here, the message engine, that needs to support cross-triggering, runtime cross-triggering, as well as transferring of data to and from the modules. And you need to support visualization of both, of all the cores, be it RISC-V, be it ARMs, in one cockpit. So this is an example of one cockpit that we have that shows ARM, very simple programs running on the ARMs and the RISC-V, but in one cockpit. So that's the run control. We need to be able to, this is probably slightly overkill, but we're monitoring the master and slaves to the NOCs. The monitors need to be truly transaction and protocol aware. And for this, with these in mind, you can do things like this. So you can look for deadlock or timeouts here. You configure this bus monitor to look for transactions going by. And if the transaction takes more than a certain number of cycles, which you can configure at runtime, then the traces that you captured or taken a copy of is available either to send off chip or for something on chip to look at. So in this case, CHI is a credit-based NOC. And so here, with this NOC here, we can look at the duration of the cache traffic coming from this processor. And from observing, because it's protocol aware, you can say, give me the min, max, and average cache misses, cache miss duration, which you can, the data that's generated, you can then use to plot a bar chart like this at runtime while the system's running. Snoop data here, well, if we observe traffic here, here, and here, we can see this is observing a lot of snoop from processor 0, which implies that actually the data is not, you might want to share the data differently. So, and because that's happening, the bandwidth that this CPU will see will be somewhat reduced. In the NOC, you might want to have observability inside the NOC. And in this case, the NOC monitors will be protocol aware, but they won't track outstanding transactions because the number of outstanding transactions in the NOC itself will be unbounded, and the NOCs will be huge. The monitors will be huge. And so, just to reiterate, that all these NOCs use a private. So all these monitors use a private interconnect, so it's not affecting the target system's behavior. And in this way, an example here is that we can see this, by observing the credits that this sees flying by, it implies that this is seeing W data and seeing a lot of contention on W data and a lot of snoop. But actually, if you look inside here, you'll see it's actually W data that's causing the stalling. So here's a cockpit that shows both run data, process-centric data, and the data that comes from the monitors in one cockpit. This is what you want to see. You don't want to have separate for the SoC, separate for the cores. You also want to be able to have a scriptable approach because you don't always have access to a GUI, or some people don't like GUIs. The data coming off these, the monitors and complex systems, what you want to be able to do is anomalous detection autonomously. The amount of data, even though it's rich, will still swamp most engineers' brains, certainly mine. So what we do is, in this case here, we've got a couple of processors, three processors, and we're taking those monitors and just looking at the latency of the of the cache traffic. And what we do here is each CPU has different cache misses, and we're observing the latency by those monitors, and the data that's being generated is just the latency in a window of time, and we're running a statistical anomaly detector. And what this is showing that these two CPUs are suffering from a lot of anomalous cache latencies. Here, this is taking the sideband signals of the cores, so the two ARM cores and the CPU, the RISC-V, looking at the sideband signals with our logic analyzer, and we're providing a non-intrusive profiler. And then that data that's coming off that we're observing, you can see the threads that are the thread switching happening inside the cores, and you can then run an anomalous detector on top of that, which in this case is showing that shown by the red dots, saying that these processes take far too long, that these threads are taking too long. But the other thing you can do is use this as a signature of the target system behaving correctly or incorrectly. And so if you ignore the red spots and say that's a working system, you can use that as a signature, and when that signature changes, you know that the system is misbehaving. And because you're monitoring other parts of the system, the SoC, you have the historical data, and so you can loop back and say, this is what caused it. So you can do anomalous detection and causality. So just to finish up, the challenge today is systemic complexity. So we need architectural and modeling tools that help with that, but that's not enough. We need to be able to do monitoring at runtime. We need tools that support true heterogeneous systems. They need to be both open source and commercial. In addition to run control, we need non-intrusive monitoring. And then more complex systems will need autonomous causality detection. And by the way, UltraSoft either provides all of this or is working on these. That's it. Thank you.